Alright, so before we begin with this exercise, full disclosure, I'm actually at a hotel room right now because I'm at a conference type, well, it's more of a short course thing. So that means I'm at a hotel and the walls aren't super thick, so you're probably going to hear people. I'm also right by an airport, so you're likely to hear planes. It's going to be really noisy, but we'll still be able to get through it. Alright. So we're talking about lower semi-continuous functions. So we want to show that function is lower semi-continuous if and only if this condition is held. Speaking of planes, I think here's one coming. Anyways, so let f from r to r, this isn't specified in the problem, but it's implied. So let this be a lower semi-continuous function. We want to prove that f less than or equal to a is going to be closed for every a and r. Given a, suppose that we have some sequence which is contained in this set of points which evaluate to a number less than or equal to a. Okay, so what we're doing is we're proving that this is a closed set, so we got to prove that that this set contains all of its limit points. So suppose this is a subset here, and suppose that these xn's converge to some x. So we must show that x is contained in this set. Alright, so how are we going to do this? First, and this is something that's going to be useful throughout this problem. So we're going to define b epsilon 0 of x as basically the open ball of radius epsilon centered at x. So this is all sets of all points y such that y is not equal to x, and the distance between y and x is less than epsilon. Okay, so why have I defined this? Recall that the lim_inf is usually defined as n goes to infinity. If we to define it as y goes to x, recall that this definition of fy is just the limit as epsilon decreases to 0 of the infimum over all points y in this punctured ball of radius epsilon of f of y. Okay. Now we know that f of xn is less than or equal to a for every single natural number n. So for any subset a contained in this sequence, i.e. for any subsequence, the infimum over this subsequence of f of y is also going to be less than or equal to a. Because this f of xn less than or equal to a, it holds for every single point in this set. So when you take the infimum is also going to be less than or equal to a. Alright. So then for all epsilon greater than 0, the infimum over all y in this punctured ball, f of y, well, this is certainly going to be less than the infimum over all y in this punctured ball intersected with the sequence of xn's of f of y. And this is because if you take an infimum over a smaller set, then you're going to end up with something that could only possibly be larger than what you started with. Okay. But now if we look at this punctured ball intersected with the sequence of xn's, this is a subset of the sequence of xn's. It's a subsequence. And so by what we just proved in the previous sentence, this is going to be less than or equal to a. And since f is lower semi-continuous, we know that f of x, by definition, is less than or equal to the lim inf yeah, I actually skipped a step, but I'll be able to sort of combine it into here. The lim inf as y goes to x of f of y. But recall, this is just the limit as epsilon decreases to 0, the infimum over all y in b epsilon 0 x of f of y. And now, for every single epsilon, we've proven that the infimum over all y in this punctured ball of f of y is less than or equal to a. And so, if you take the limit as epsilon goes to 0, you basically end up taking the limit as epsilon goes to 0 of both sides of the inequality in the previous equation. And so on the left-hand side, you end up with the lim inf, and then on the right-hand side, you're taking the limit as epsilon decreases to 0 of a, which is just a. So this is less than or equal to a. And so f of x is less than or equal to a, which means that x is contained in set of all points which evaluate to a number less than or equal to a. And hence, this proves that this set, f less than or equal to a, is closed for all a in R, because it contains all of its limit points. And that's one of the directions that we wanted to show, that if f is lower semi-continuous, then this set is closed. But now we need the other direction. So conversely, suppose that this set is closed for all real numbers a. Now, given any x in R, remember, what are we trying to prove? We're trying to prove for any x in R that f of x is going to be less than or equal to the lim inf as y approaches x of f of y. So to get to that, so given any x in R, let a be some number which is less than f of x. Then y, all points y such that f of y is greater than a, well, this is equal to the complement of all points y such that f of y is less than or equal to a, and so it's the complement of a closed set, and so it's open. So this is open, and furthermore, it does not contain x. Wait, no. It does contain x. I sort of got mixed up when I was writing this proof. And contains x. So there exists an epsilon prime, a positive number epsilon prime, small enough that the punctured ball of radius epsilon prime centered at x is entirely contained in f greater than y, because this is an open set which contains the point x. And this also, I guess, uses the fact that and this is something that comes from analysis, and you can prove it if you want, but that any open set in the standard topology on R can be written as a countable union of disjoint open intervals. And it's actually sort of unfortunate, because the first time I encountered this fact, it was in an analysis course where I was expected to know it and use it on an exercise. So even though I had never been taught it before. So this is another one of those things that, like, it might not come up in a course naturally, but at some point you're just expected to know it. So if you haven't seen this, it might be useful to look it up. But yeah, anyways, so there is an epsilon small enough that this ball is entirely contained in the set F greater than A. So now, if we have some subset A of this punctured ball, then the infimum over all elements of the subset is going to be greater than or equal to A. Because for every point in this set evaluates to a number which is strictly greater than A. And so if you take the infimum over a whole bunch of these, all of these points will evaluate to something which is greater than A. However, they could be getting closer and closer to A, so this infimum could be exactly A, but it's certainly going to be greater than or equal to A. It can't possibly be less than A, because if it were less than A, then there would be some point which evaluates to a number which is less than or equal to A, and that's not possible by the definition of the set. Okay, so then this infimum is greater than or equal to A. So now, what we have is the lim inf as y goes to x of f of y is the limit as epsilon decreases to 0 of the infimum over all y in ball of radius epsilon 0 of x of f of y. But because you're taking epsilon to be smaller and smaller, we can assume that this limit is certainly going to be the same if we take the limit over all epsilon such that epsilon is less than epsilon prime of this infimum over y in b epsilon 0 x of f of y. Forgot to put parentheses here. Okay, so we're taking the limit as epsilon decreases to 0, epsilon strictly less than epsilon prime. So this is actually, so the ball of radius epsilon centered, or the punctured ball of radius epsilon centered at 0, whenever epsilon is less than epsilon prime, this infimum is going to be greater than or equal to A, because of what we just proved in the previous sentence. And so we're taking the limit as epsilon goes to 0 of A, which is just going to be A, because this no longer depends on epsilon. Now this is sort of interesting. This holds for all A less than f of x, so taking the limit as A increases to f of x in this inequality that we've shown yields the lim inf as y approaches x of f of y. Really, this is the limit as A increases to f of x of the lim inf as y approaches x of f of y. But that doesn't involve A at all. So this is just lim inf as y goes to x of f of y. This is going to be greater than or equal to the limit as A increases to f of x of f of, no, this limit as A increases to f of x of A, but this limit is precisely f of x. So this is sort of neat because we have something that we wanted something to hold with a greater than or equal to, and we prove that it holds, we want to prove that this lim inf is greater than or equal to f of x, but we were only able to prove that it holds greater than or equal to A for any A which is strictly less than f of x. But because it holds for any A which is strictly less than f of x, we can just take the limit as A increases to f of x. So yeah, this is sort of neat because usually you can't like use this sort of technique to get around limits, but sometimes it works. Because sometimes like if something like this could work, you'd expect that you could sort of get at f of x immediately without having to introduce this a, although I guess that's not necessarily true because you can do it here. Yeah, I don't know. This is sort of neat. I don't know. I like this sort of analysis stuff. Alright. And this is what we want. We want this limit as desired. Or rather, yeah, because that's exactly the thing that we wanted to prove. We wanted to prove that this inequality holds for all x, and we've proven that it holds for all x in R. Because we've chosen an arbitrary x in R, and we've proven that it holds. Alright. Alright, so what we want to do now is, like, why do we care about these conditions? What we really care about is that semi-continuous functions are measurable. So, finally, suppose f is lower semi-continuous, then for all a in R, the set of all points where f is less than or equal to a, which is f inverse of minus infinity a, is closed. So what this tells us is f inverse of minus infinity to a is contained in the Borel sigma algebra on R. And so this holds for any for any interval of the form, any closed interval from negative infinity to a, not including minus infinity, of course. But recall that the sigma algebra generated by sets of this form, minus infinity a in R, is entirely, this gives you the entire Borel sigma algebra. Because if you take, because what you need to generate the Borel sigma algebra is you need to have all open intervals. So let's say you have an open interval of the form a, b. Then what you can do is you can take the closed interval from minus infinity to a, take its complement, so that's the open interval from a to infinity, and you take its union with minus infinity to, no. So here, what do you do here? So we have open intervals of this form. And this should give you all open intervals. Yeah, because sets of this form will generate all of the open sets. I'm just sort of blanking on the details. I think what you have to do I think you have to use either like a countable union I think you have to use some sort of, oh wait, no, we have countable intersections. Duh. Okay. So what we do is you can just take, you can certainly take the open interval from A to B. Okay. So we take this minus infinity to B. Plus 1 over n complement. And then we have to take the intersection over all n, all natural numbers n. Because what's going to happen here is we're going to get a to b plus 1 over n closed, but then when we take the intersection over all n, all natural numbers n, we're going to end up with just the open interval from a to b. Right, let me just make sure. Okay, so you take the complement of this and you get open interval from b plus 1 over n to a. So right, okay, yeah, exactly. This intersection is going to be precisely the intersection, so this is equal to the intersection over all natural numbers n of the half open interval from a to b plus 1 over n, which is precisely that this entire intersection is precisely the open interval from a to b. So this generating set contains, well, the sigma algebra generated by this collection contains all open intervals, and so it contains the Borel sigma algebra. And certainly all these sets here are contained in the Borel sigma algebra, and so it's precisely the Borel sigma algebra. I think this is actually like, this should be something that we've talked about in this section. If not, it's something that's definitely it's a theorem in Fallon that you can look at if you want. Okay, so since this sigma algebra is precisely all of R, we know that F inverse of A is going to be in R for all Borel sets A. Right? Because the inverse image of a generating set is in R. So the inverse image of the entire set is in R. I think this also uses a lemma that we proved in a previous exercise, which is that to prove that a function is measurable, it suffices to prove that it's measurable when you take the inverse image of a generating set of the sigma algebra in the codomain. Okay, so thus f is measurable. I'll just write this. And because, yeah, this is precisely the definition of measurable. You need the inverse image of any measurable set to be measurable. But we don't just need that lower semi-continuous functions are measurable. We need semi-continuous functions, meaning we need upper semi-continuous functions to be measurable. Similarly, suppose f is upper semi-continuous. This means precisely, by definition, that minus f is lower semi-continuous. So, for all a in R, the set of points where minus f is less than or equal to a is closed. But this is also, if you just multiply the minus sign, this is f greater than or equal to minus a. So this is f inverse of minus a to infinity is closed, and thus belongs to R. But then the sigma algebra generated by all of these types of intervals is for almost the same exact reason as before. And so f is measurable because the inverse image of a generating set belongs to the sigma algebra, and so the inverse image of the sigma algebra belongs to the sigma algebra. Alright, and yeah, that's all we need to prove. There are some details here that I left out, like, well, no, I went through this detail of why this is a generating set. But yeah, this is how you do this exercise, and this is an introduction to lower semi-continuous functions, and so now we are done.